So now we are going to study the case 2. Suppose if for that voltage control of unequal PWM for that single phase full bridge inverter. So I am going to switch on the switch 1 and switch 2. So if I turn on the switch, so basically now as I am going to turn on the switch 3 and switch 4, so therefore V0 is equal to minus 0.5 VDC and VB0 is equal to plus 0.5 VDC. So VAB is equal to V0 minus VB0, so we are going to get minus VDC from 0 to alpha. So from alpha to 90, from alpha to 180 minus alpha, I am going to turn on the switch 1 and switch 2. So therefore V0 is equal to plus 0.5 VDC and VB0 is equal to minus 0.5 VDC. So VAB is equal to plus VDC. Similarly from 180 minus alpha to 180, I am going to turn on the switch 3 and switch 4. So therefore V0 is equal to minus 0.5 VDC, VB0 is equal to plus 0.5 VDC. So VAB is equal to minus VDC. Similarly from 180 to 180 plus alpha, I am going to turn on the switch 1 and switch 2. So therefore again V0 is equal to plus 0.5 VDC, VB0 is equal to minus 0.5 VDC. So VAB is equal to plus VDC. Similarly from 180 plus alpha to 360 minus alpha, I am going to turn on the switch 3 and switch 4. So VA0 is equal to minus 0.5 VDC, VB0 is equal to plus 0.5 VDC. So VAB is equal to minus VDC. Similarly from 360 minus alpha to 360, I am going to turn on the switch 1 and switch 2. So V0 is equal to plus 0.5 VDC, VB0 is equal to minus 0.5 VDC. So VAB is equal to plus VDC. So this is the way that you are going to get. So you can see clearly negative pulse width and a positive pulse width of different nature. So that is the reason it is called as the unequal pulse width modulation. So if you turn on the switch 1 and switch 2, the VAB is equal to minus, VAB is equal to plus VDC. If you turn on the switch 3 and switch 4, then we are going to get VAB is equal to minus VDC. So by doing the switching process, then we are going to get this type of voltages we are going to get. You can see clearly now alpha is nearly equal to 0 degree here in this case. So now I am going to analyze these graphs. So V0, VB0 and VAB, all these are going to satisfy the odd function property of wave symmetry and also quarter wave symmetry. And I have already told you from the graph you can see that alpha is very near to 0 degree. So then I want to find what is the Fourier series expansion of this V0. As it is an odd function, so A0 is equal to 0, An is equal to 0, and it is also going to satisfy the half wave symmetry and quarter wave symmetry. So only in the Bn it is not equal to 0 only for odd harmonics. So therefore sigma n is equal to 135 up to infinity Bn sin n omega t. So I want to find what is the value of Bn. General expression is 2 by 2 pi integration of 0 to 2 pi f of theta into sin n theta into d theta. But I want to find only now B1, so keep substitute here n is equal to 1 here. So 2 by 2 pi integration of 0 to 2 pi f of theta into sin theta into d theta. As it is going to satisfy the quarter wave, so I am going to do only from 0 to 90 degree, so into multiply by 4. So now 0 to pi by 2, you can split into two parts, 0 to alpha and alpha to pi by 2. So 0 to alpha, its value is minus 0.5 VDC, and from alpha to pi by 2, its value is plus 0.5 VDC. So if you solve this one, finally we are going to get 2 VDC by pi into 2 cos alpha minus 1. I want general expression Bn. So 2 VDC by n pi 2 cos n alpha minus 1 is the general expression of the Bn. So I can substitute this in the V0. Finally I am going to get V0 is equal to sigma n is equal to 135 up to infinity 2 VDC by n pi 2 cos n alpha minus 1 into sin n omega t. So this is the general expression of V0. Similarly I want the value of VB0 expression. Just it is a phase shift of 5. So therefore sigma n is equal to 135 up to infinity 2 VDC by n pi 2 cos n alpha minus 1 into sin of n omega t minus n pi. Similarly I want to find what is the value of the expression of the VAB. So VAB is equal to V0 minus VB0. So simply we are going to get sigma n is equal to 135 up to infinity 4 VDC by n pi 2 cos n alpha minus 1 into sin n omega t. So this is the expression that we are going to get finally. So sigma n is equal to 135 up to infinity 4 VDC by n pi 2 cos n alpha minus 1 into sin n omega t. So now I want to find what is the peak value of the fundamental component of the VA0. If we substitute n is equal to 1, we are going to get 2 VDC by pi into 2 cos alpha minus 1. So this is the peak value of the fundamental component of the VA0. As alpha is nearly equal to 0, I want to change from alpha is equal to 0 to 60 degree. I want to see what is the value. If alpha is equal to 0, if I substitute here, I am going to get 2 VDC by pi. If I substitute alpha is equal to 60 degree, I am going to get its value is 0. So whenever the alpha is varying from 0 to 90 degree, the peak value is going to vary from 2 VDC by pi to 0. So now we are going to study the case 3. So now we are going to switch on. So now we are going to switch on from 0 to alpha 1. We are going to switch on the switch 1 and switch 2. So whenever we are going to switch on the switch 1 and switch 2, so therefore we are going to get V0 is equal to plus 0.5 VDC and VB0 is equal to minus 0.5 VDC. So VAB is equal to plus VDC. From alpha 1 to alpha 2, we are going to switch on the switch 3 and switch 4. So V0 is equal to minus 0.5 VDC, VB0 is equal to plus 0.5 VDC and VAB is equal to minus VDC. Similarly, from alpha 2 to alpha 3, again we are going to switch on the switch 1 and switch 2. So therefore again, then we are going to get V0 is equal to plus 0.5 VDC, VB0 is equal to minus 0.5 VDC. So therefore VAB is equal to plus VDC. Similarly, from alpha 3 onwards, so from alpha 3 onwards, we are going to do this type of switchings. So alpha 1, alpha 2 and alpha 3 are this less than 90 degree. So this is the pattern that we are going to follow in order to make this switching process. So therefore we are going to get this type of voltages. So only thing is, you have to remember, when I turn on the switch 1 and switch 2, V0 is equal to plus 0.5 VDC and VB0 is equal to minus 0.5 VDC. So VAB is equal to plus VDC. If I turn on the switch 3 and 4, then V0 is equal to minus 0.5 VDC and VB0 is equal to plus 0.5 VDC. So VAB is equal to minus VDC. So this is the pattern that you need to remember. So this is the way of switching goes and happens. So alpha 1 and alpha 2 and alpha 3 are, everything is less than 90. So you can see clearly that whenever you are, you have to start your journey from starting onwards. So whenever you are going from high to low means negative. Again you are going from low to high means positive. Again you are going from high to low means negative. So this is the thing that you need to remember. So always whenever you are going from high to low means negative, see, low to high means positive, again high to low means negative. So this is the pattern that you need to remember. As I already told you, VA0, VB0 and VAB, these are odd functions, and also half wave symmetry and quarter wave symmetry are satisfied by these functions. So V0 is equal to sigma n is equal to 135 up to infinity Bn sin n omega t, because odd function means n is equal to 0, n is equal to 0 and Bn is not equal to 0 only for odd harmonics. So now I want to find what is the value of this Bn. So this is a Bn I want to figure out. So here Bn is equal to 4 into, so remember only thing, the basic formula, which is Bn is equal to 4 into the peak value is VDC by 2 by n by into. So always the starting is higher, so plus 1. So from high to low you are going to go, so minus 2 cos n phi 1. Again you are going from low to high at alpha 2, so plus 2 cos n alpha 2. Again you are going from high to low at alpha 3, so minus 2 cos n alpha 3. So this is the function you are going to get. So listen carefully. So Bn is equal to 4 into peak value is VDC by 2 by n pi. The starting is higher, so 1. It is going from high to low means minus 2 cos n alpha 1. Again going from low to high means plus 2 cos n alpha 2. Again going from high to low means negative, so minus 2 cos n alpha 3. So this is the function, this is the Bn that you are going to get. So you can substitute this Bn in this value, then you are going to get V0. Similarly, VB0 is equal to, see, Bn is not all going to change. The only thing is here. So sigma n is equal to 135 up to infinity b n sin n omega t minus n pi. This is the V naught. So whereas VAB is equal to sigma n is equal to 135 up to infinity. So simply we are going to get 2 times of Bn sin n omega t, because it is a 4 VDC by n pi. So everything is same. So this is the thing that you need to remember. So the general format of any Fourier series coefficients is Bn is equal to 4 into peak values VDC by 2 by n pi. Here higher means plus 1. So higher means plus 1. While it is going from high to low, so minus 2 cos n alpha 1, from low to high means plus 2 cos n alpha 2, again high to low means minus 2 cos n alpha 3. So this is the format that you need to always remember the basic function. So now we are going to study about the disadvantage in one switching in quarter. So what is the disadvantage of only one switching operation is done in quarter, means in only 90 degree. In 90 degree, if we do only one switching operation, then what is the disadvantage we need to study? So single pulse width modulation. I have already told you, the single pulse width modulation, the Fourier series coefficient value is nothing but 4 VDC by n pi sin nd into sin n pi by 2. So this is the thing that you are going to get. So Dn is equal to 4 VDC by n pi sin nd into sin n pi by 2. So if you substitute n is equal to 1, n is equal to 1, we are going to get 4 VDC by pi into sin d. So 4 VDC by pi into sin d. This is the expression that you are going to get. Now, to remove the third harmonic, if you want to remove the third harmonic, then what you have to do? Sin 3d is equal to 0, because sin nd is equal to 0. So therefore, sin 3d is equal to 0. So therefore, now if you substitute here, 3d is equal to pi k. So therefore, 2d is equal to 2 pi k by 3. So therefore, you are going to get finally, this is the expression, 2d is equal to 120 degree. So at 120 degree, you are trying to remove the third harmonic. So you are removing the third harmonic at 2d is equal to 120 degree. So now I want to find what is the value of this B1, the fundamental harmonic peak value at 2d is equal to 120. So if you substitute here, we are going to get, it's a very small value. So at 120 degree, we are going to remove the third harmonic, and also we are going to get the fundamental component of very small value. Suppose for case 1, we will see. So what happens for case 1? So already we have studied the case 1, case 2 and case 3. So for case 1, what is going to happen? So there, the Fourier series coefficient is nothing but 4 VDC by n pi 1 minus 2 cos n alpha. That is the thing that you are going to get for VAB, the expression of VAB. So therefore here, Bn is equal to, means output voltage, Bn is equal to 4 VDC by n pi 1 minus 2 cos n alpha. As I already told you, in the case 1, the alpha is going to lie from 60 degree to 90 degree. So to remove the third harmonic, what I should do? 1 minus 2 cos 3 alpha is equal to 0. So finally I am going to get alpha is equal to 20 degree. So this is the 20 degree I am going to get. But 20 degree cannot be possible because alpha should be 60 to 90. So therefore you cannot remove the third harmonic for case 1. So it is always going to get present. So not possible. Now we will see the case 2. The output voltage Fourier series coefficient Bn is equal to 4 VDC by n pi 2 cos n alpha minus 1. So 2 cos n alpha minus 1 we are going to get for the second case. So for this, what is going to happen? So for this, I have already told you alpha is going to lie from 0 degree to 60 degree in the second case. So to remove third harmonic in the second case, then I definitely have to equate 2 cos 3 alpha minus 1 is equal to 0. So here alpha is equal to 20 degree. Yes, alpha is nearly equal to 0 because it is lying between 0 to 60 degree. So therefore we can say simply alpha is equal to 20 degree is possible. So if I substitute, if I want the value of the fundamental component of the output voltage, the value peak value, fundamental peak value of the component, the fundamental peak value of the output voltage in this second case, if I substitute to eliminate the third harmonic, I am going to get a very small value. So only in the single pulse width, in the case 1 and the case 2, there is only one switching in the 90 degree. So we have studied the important aspects of these things. So now we are going to study about the selective harmonic elimination. We are going to study this concept. So basically, Suppose if I do the two switching in quarter cycle, so in 90-degree, if I do the switching two times, then what is the things we are going to get? We are going to see this one. So if I do the switching two times in 90-degree, then what is the advantages and each and everything we are going to see. See, if I do the switching like switch on A and B, then V0 is equal to plus 0.5 VDC. And if I switch on switch 3 and switch 4 from alpha 1 to alpha 2, then I am going to get V0 is equal to minus 0.5 VDC. Similarly, so you have to go this procedure. So whenever you turn on the switch 1 and switch 2, V0 is equal to plus 0.5 VDC. And if you turn on the switch 3 and switch 4, then V0 is equal to minus 0.5 VDC. So this is the nature of the pole voltage V0 we are going to get. So now we are going to do some more analysis. The only thing is there are two types of this. There are two switchings are present in the 90-degree in the quarter cycle. So now this V0 signal we are going to do some analysis, as V0 is an odd function and also half wave symmetry and quarter wave symmetry. All these things are going to satisfied by this function. So therefore V0 is equal to sigma n is equal to 135 up to infinity Vn sin n omega t, because as it is an odd function, a0 is equal to 0 and n is equal to 0, and it is also going to satisfy its half wave symmetry and quarter wave symmetry. So Bn is not equal to 0 only for odd value of the harmonics. So if I want the value of Bn, which is 4 times the peak value is VDC by 2 by n pi into, here the first is a positive, so plus 1. Again it is going from plus to minus means minus 2 cos n alpha 1. Again going from minus to plus means again plus. So plus 2 cos n alpha 2. So this is the thing that you need to remember, only up to 90-degree. So below 90-degree only you have to consider these things. So the first is a positive, so plus 1, and it is going from high to low at alpha 1, so minus 2 cos n alpha 1, and it is going from minus 2 plus means it is a plus 2 cos n alpha 2. So this is the value of the Bn. So if you want the peak value of the fundamental component, substitute n is equal to 1, we are going to get, this is the expression that we are going to get if we substitute n is equal to 1. So this is called as the fundamental component of the, or peak value of the fundamental component of the V0. So now here let me assume the fundamental peak value is 0.8 into 2 VDC by pi. I want this type of value, which is 0.8 into 2 VDC by pi. So if I equate these two values, I am going to get 0.8 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2. Means I need the fundamental peak value of this nature, which is 0.8 into 2 VDC by pi. Then I am going to get relation with respect to alpha 1 and alpha 2. This is the relation I am going to get. So now we will see the boundary conditions. As I have already told you, x-axis, let me take alpha 1 and alpha 2 is the y-axis. As I have already told you, alpha 1 and alpha 2 are less than 90-degree, and alpha 1 is less than alpha 2 and alpha 2 is less than 90-degree. And here let me take the boundary conditions, both are equal. Alpha 1 is equal to 0 and alpha 2 is equal to 90. So these are the boundary conditions. Alpha 1 is equal to alpha 2 and alpha 1 is equal to 0 and alpha 2 is equal to 90-degree. These are the boundary conditions. So here when alpha 1 is equal to alpha 2 means I am going to get a straight line. So therefore here alpha 1 is equal to alpha 2 means a straight line, and alpha 1 is equal to 0 means I am going to get this line. And alpha 2 is equal to 90 means I am going to get this line. So this is the boundary region. So this is the region where we are going to operate. So this is the region where alpha 1 is less than alpha 2 and alpha 2 is less than 90-degree. So this is the region where alpha 1 is less than alpha 2 and alpha 2 is less than 90-degree. This is the region we are need to choose a particular value of alpha 1 and alpha 2. So this is called as the operating region. So let me assume that the fundamental peak value. Let me assume the fundamental peak value of V0 is equal to 0.92 dc by pi, and the fundamental is the peak value of the third harmonic of V0 is equal to 0. Then we get. See, I am going to assume another case in which I want a peak value of 0.92 VDC and the third harmonic as 0. Then I have to substitute these two equations. Then finally I am going to get. So now we are going to get these two equations. So these are the Fourier series fundamental. These are the Fourier series coefficients. So therefore now, if you solve these two equations with two unknowns, we can get the value of alpha 1 and alpha 2. So with this help of alpha 1 and alpha 2, you are going to remove the third harmonic, and also you are going to get the fundamental component of peak value 0.92 dB. So therefore, we can say that let Va0, see this is by this way we can get the value of alpha 1 and alpha 2. Let me take another case. Let I want a fundamental peak value of voltage of 0.92 dC by pi, and I want the fifth harmonic value. The fifth harmonic peak value I want to 0. Then what is the case? Again, by using the Fourier series coefficients, you are going to get two equations. So these are the two equations. Yes, I want the basically fifth harmonic to be 0, and the peak value of the fundamental component of the V0 I am going to get 0.92 dC by pi. So by solving these two equations, I can get the value of alpha 1 and alpha 2. So this is the way, by choosing this alpha 1 and alpha 2, we can say that we can remove the fifth harmonic component also and get the peak value of fundamental as 0.92 dC by pi. Advantage of this one is, here true switching in quarter cycle means what is going to happen basically means whatever the frequency, whatever the harmonic that we don't want, we can easily make it happen with the help of this process. So selective harmonic elimination means whatever the harmonic that we don't want, we can remove it in a very easier manner with the help of this two-way switching. Whereas this is not at all possible. The selective way of it is not possible in the one-way switching. So one-way switching in quarter cycle, this type of selection is not present, that you can already see. So this type of selection is not possible in one type of switching in quarter cycle. Whereas in this two switching in quarter cycle, yes, we can eliminate whatever the harmonic that we really don't want. So therefore, we can eliminate this process. So this is the process by which we can eliminate whatever the frequency harmonic that we don't want in the output voltage. And this is the beautiness of this one. So more the switching, more the harmonics that we can eliminate, it is in our control. So now we are going to study the sinusoidal pulse width modulation. So bipolar. Sinusoidal pulse width modulation we are going to study in a very detailed manner, especially the bipolar part. So you can see clearly, here we are going to take the reference signal as a sinusoidal. Here we are going to take the reference signal as a sinusoidal, whereas the carrier signal is a triangular waveform. So this is the format we are going to take here. So we are going to compare these two signals, and then we are going to generate the triggering pulses. So based on that, we are going to get the output voltages. I have already told you, whenever the carrier signal is higher, whenever the carrier signal is higher than the reference signal, then definitely you have to trigger. So whenever the carrier signal is greater than the, or simply we can say in another format also, suppose if the reference signal is greater than the carrier signal, then we have to trigger the switch 1 and switch 2. So therefore, Va0 is equal to 0.5 VDC and Vb0 is equal to minus 0.5 VDC. So therefore, Vab is equal to plus VDC. Similarly, whenever this is the case only thing. Suppose if the reference signal is lesser than, carrier signal, then trigger the S3 and S4. So then trigger the S3 and S4. So therefore, Va0 is equal to minus 0.5 VDC and Vb0 is equal to plus 0.5 VDC and Vab is equal to plus VDC. So this is the way that you are going to get this circuit. So whenever the reference signal is greater than carrier signal, trigger the S1, S2. So V0 is equal to plus 0.5 VDC, Vb0 is equal to plus 0.5 VDC. So Vab is equal to plus VDC. Suppose if the reference signal is lesser than carrier signal, then trigger the S3, S4 switch. So therefore, we are going to get Va0 is equal to minus VDC by 2, Vb0 is equal to minus plus VDC by 2, so Vab is equal to minus VDC. So you can see clearly here, you are going to get a positive pulse and also negative pulse. So you are going to get a positive pulse and also negative pulse in a given half period. So in a given half period of 180, you are going to get a positive pulse and negative pulse. So therefore it is called as a bipolar. So now we are going to do some more analysis of this circuit. So here I am going to take the reference signal as sinusoidal. So Vr of t is equal to Vm sin omega t. Similarly, carrier signal I am going to assume it as a triangular waveform, which is a Vc of t. So Vm is the peak value of the reference signal, and Vc is the peak value of the carrier signal. whenever the reference signal is greater than carrier signal, I've already told you, whenever the reference signal is greater than carrier signal, then switch on the S1 and S2. So therefore V0 is equal to VDC by 2, VB0 is equal to minus VDC by 2. So therefore VAB is equal to plus VDC. So if V reference of signal is lesser than carrier signal, then on the S3, S4, so therefore V0 is equal to minus VDC by 2 and VB0 is equal to plus VDC by 2 and VAB is equal to minus VDC. So always VAB is equal to V0 minus VB0. And I've already told you FR is called as the frequency of the reference signal and FC is called as the frequency of the carrier signal. Always the frequency of the carrier signal is always greater than the frequency of the reference signal. And I've already told you the output signal frequency is equal to frequency of the reference signal. So whereas if you are going to increase the number of frequency, if you try to increase the carrier signal frequency, then the number of pulses in a given half cycle are going to get increased. So you can see from the diagram that DA0, VB0 and VAB, all these things are going to satisfy odd function, half wave symmetry and quarter wave symmetry. So now we are going to analyze the diagram part. This is called as let me take a small section. So in this section, this is a triangular waveform. So this is a triangular and this is a sinusoidal. So let me take a points A, B and C. This is D, A, B, C, D, E, F. So these are the points I am going to consider. It is going from 0 to plus VC and this is like this one. So you can see clearly here VR of t is greater than. So VR of t is greater than VC of t in this region from A to B. So therefore here that VR is equal to plus VDC by 2. Whereas here VR of t is less than VC of t. So therefore VR is equal to minus VDC by 2. So this is the thing that I am going to analyze only in this section. So in this section VR of t is greater than VC of t. So therefore V0 is equal to plus VDC by 2. Whereas here VR of t is less than VC of t. So therefore minus VDC by 2. So let me consider this period as a T on and this is T off. So overall width is Ts. So Ts is the overall width. This is T on and this is T off. So overall width is Ts. So I want to find what is the average value of the V0 in that section only. I want to find what is the value of the average value only in that section. So therefore here area plus VDC by 2 into T on minus VDC by 2 into T off. My total period is T on plus T off. So Ts is called as the T on plus T off. So therefore, I have already told you that duty ratio is equal to, duty ratio is nothing but T on by Ts. So duty ratio is equal to T on by Ts. So T on is equal to D into Ts, whereas T off is equal to 1 minus D into Ts. So therefore, this is the way we are going to study this in the chopper concept. So therefore, Ts is called as a T on plus T off. Duty ratio is a T1 by Ts. So therefore T off is equal to 1 minus D into Ts. So you can substitute all these things in this above relation and then you can convert in terms of D. So therefore replace T on is equal to D into Ts and replace T off is equal to 1 minus D into Ts and simply T on plus T off is equal to Ts. So if you substitute here we are going to get finally VA0 average is equal to VDC by 2 into 2D minus 1. So this is the value that we are going to get. The average value of the output signal in that section only, which is VDC by 2 into 2D minus 1. So D is nothing but T1 by Ts, duty ratio T1 by Ts. So T1 is nothing but it is nearly equal to AB, whereas TC is nearly equal to AC. So this T1 is nearly equal to this with AB and Ts is nearly equal to with AC. So AB by AC is equal to. So here AB by AC is equal to, simply we can say that AB by EF, because AB by AC is nearly equal to AB by EF because AC width is nearly equal to EF also, AB by EF. Again it is equal to AE by DF because the two triangles are similar, which is the ABE and DEF, ABE and DEF are similar triangles. So ABE and EF are similar triangles. So ABE and DEF are similar triangles. So ABE and DEF are similar triangles. So simply we can say that AB by AC is nearly equal to AB by EF. So therefore AB by EF is nearly equal to, again simply we can say that AE by DF. So AE by DF. So AB by EF is equal to AE by DF with the help of two triangles are similar, which are ABE and DEF. So now I want to find what is the value of AE. I want to find what is the value of AE. So AE is equal to VR of T plus VC. So you can see from graph AE is equal to, so AE is equal to, AE is equal to, simply I can say that AE. So what is the value of AE? VR of T plus VC. So you can say clearly this is plus VC and this is minus VC. So this is the base 0. So as it is going from plus VC to minus VC, so it is a straight line, it is a straight line going from minus VC to plus VC. So minus VC to plus VC I am going to consider. So minus VC to plus VC, and this is the base value. This is called as a base, reference base, 0 axis, and this is the sinusoidal signal. So therefore now AE is equal to, the magnitude AE is equal to, this length is VC and this is VR of T. So therefore AE is equal to VR of T plus VC, whereas DF is equal to, EF is equal to VC plus VC, which is 2VC. So therefore AE is equal to VC plus VR of T and DF is equal to 2VC. So AE is equal to VR of T plus VC and DF is equal to 2VC. Now AE is equal to VR of T plus VC and DF is equal to VC. So you can substitute in this equation. Finally we are going to get D is equal to, AE is equal to VR of T plus VC by DF is equal to VC. So if you solve this one, finally we are going to get 2D minus 1 is equal to VR of T by VC. So therefore VA naught average is equal to, just now we have did, which is VDC by 2 into 2D minus 1. So in place of 2D minus 1 I am going to substitute VR of T by VC. So I am going to get VDC by 2 into, whereas VR of T is equal to Vm sin omega T by VC. So therefore VA naught average is equal to M into, so this is called as Vm by VC is called as the ratio of peak value of reference signal by peak value of the carrier signal is called as the modulation index. So M into VDC by 2 into sin omega T. So this is called as the average value of the, this is called as the average value of the VA naught. So M into VDC by 2 into sin omega T. So if you want to find what is the average value of the VB0, simply M into VDC by 2 into sin of omega T minus 180, because it's a phase difference of 180 degree. So if we want to find what is the average value of VAB, pole voltage, the line voltage, this difference of these two things, VA naught average minus VB naught average. So we are going to get M into VDC into sin omega T. So this is the thing that you are going to get. So only thing that you have to remember is M into the peak value is VDC here into sin omega T. So this is the thing that you need to always be careful. So M into VDC into sin omega T. This is the average value of the load voltage or the output voltage. I want to find what is the peak value. What is the peak value of the fundamental component? What is the peak value of the fundamental, we can say the peak value of this average value I want to figure out. It is equal to M into VDC. So this is called as the fundamental component of this line voltage, which is M into VDC. VAB1 is called as the fundamental component of the VAB. So this is called as the fundamental component M into VDC. This is called as the fundamental component of the VAB. Similarly, if you want to find what is the peak value of the fundamental component of the VA naught, it is equal to M into VDC by 2. So M into VDC is called as the fundamental, you can simply call it as the peak value of the fundamental component of the VAB, whereas M into VDC by 2 is called as the peak value of the fundamental component of the VJ naught. So now I want to write the Fourier series expansion. So basically I want to write the Fourier series expansion of this VB naught. So of this VB naught I want to write the Fourier series expansion. So you can see clearly here for this VB naught, So in 90 degree, there are alpha 1, alpha 2, alpha 3 and alpha 4. So there are four switching operations are present in 90 degree. So for VB naught, so the first is a positive, so plus 1. So therefore, the Fourier series coefficient of this VB naught is equal to Bn is equal to 4 into peak values VDC by 2 by n pi into the first is a positive, so plus 1. It is going from plus to minus means minus 2 cos n alpha 1. Again minus to plus means again positive, plus 2 cos alpha 2 n alpha 2 and again minus 2 cos n alpha 3 again plus 2 cos n alpha 4. So this is the Fourier series coefficient of this expression. So VB naught is equal to sigma n is equal to 135 up to infinity Bn sin n omega t, because it is a half wave signal, it's a odd function, half wave symmetry and quarter wave symmetry. So therefore A naught is equal to 0, An is equal to 0, Bn is not equal to 0 only for odd harmonics. So Bn is equal to, based the quarter wave symmetry, 2 by 2 pi integration from 0 to pi by 2 VB naught sin omega t into d theta into 4. So here 0 to pi by 2 we are going to write the function, we are going to split into 4 types because it is split into 4 types. So after doing that, finally we are going to get Bn is equal to 4 into the peak values VDC by 2 by n pi. Here the first is a positive nature, so plus, this is going from plus to minus means minus 2 cos n alpha 1, again going from minus to plus means plus 2 cos n alpha 2, again going from plus to minus means minus 2 cos n alpha 3, again going from minus to plus means plus 2 cos n alpha 4. So at the given alpha 1, alpha 2 and alpha 3 and alpha 4. So now I want the fundamental component to be, I want the fundamental component of VB naught is equal to 0.9 into 2 VDC by pi, and I want the third harmonic to be 0, I want the fifth harmonic to be 0 and also seventh harmonic to be 0. So these are the conditions. See, there are 4 coefficients. So these are the 4 unknowns, alpha 1, alpha 2 and alpha 3 and alpha 4. So we need 4 equations to solve. So this is the, I want these type of things. So the Fourier series, or we can say the fundamental component I need to want, which is 0.9 2VDC by pi, and the third harmonic to be 0, fifth harmonic to be 0 and seventh harmonic to be 0. Then what is the value of alpha 1, alpha 2, alpha 3 and alpha 4? So you can substitute this equation and you can get alpha 1, alpha 2, alpha 3 and alpha 4. All these things we can easily figure out, and these are all less than 90 degree. So always we are going to get the PhD in the range from 0 to 5. So because of this bipolar, we are going to get the PhD in the output voltage. It is nearly from 0 to 5%. And I have already told you the FC is called as the frequency of the carrier signal. It is always equal to 2 into K into Fr. So 2 into K into Fr, whereas K is called as the number of discontinuous in the pole voltage in 90 degree. So FC is equal to 2K into Fr. It's a general formula. So here 2K into Fr. So K is called as the number of discontinuous in the pole voltage in 90 degree. So in 90 degree, how many number of, I have already told you an important concept here. I have already told you the number of pulses in half cycle. So the number of pulses in half cycle I have already told you is equal to FC by 2Fr. So FC by 2Fr is the number of pulses we are going to get in a half cycle. So in half cycle the number of pulses we are going to easily figure out. So which is equal to FC by 2Fr. So therefore now here, so therefore if you do the manipulation, we are going to get FC is equal to, in place of M I am going to substitute K. So 2K into Fr. So FC is equal to 2K Fr. Here K is called as the number of discontinuous in the pole voltage in 90 degree. In 90 degree, how many number of discontinuous we are going to get? The number of discontinuous. So the number of discontinuous is equal to number of pulses we are going to get. So listen, the number of discontinuous means the number of pulses we are going to get. That is the meaning of this one. So now we are going to study the concept, which is the sinusoidal PWM of unipolar. Now we are going to see. So you can see clearly in 0 to pi, you can see clearly only one type of pulse is present, only positive pulse is present. So only one type of pulse, means the positive means always positive for 0 to pi. So we can say only one type of pulse is going to present, of only one type of polarity of pulse is present from 0 to pi. That is the reason it is called as the unipolar. So only one type of polarity of the pulse is present. So in the output voltage, so this is called as the unipolar. And let us now discuss the operation of this one. So now we are going to do the analysis of this signal. So I have already told you here we are going to take the reference signal as the sinusoidal signal, whereas the carrier signal as the triangular signal. So if the reference signal is greater than carrier signal, then turn on the S1. Then turn on the S1. So therefore, VA0 is equal to VDC by 2. If VR of t is less than VC of t, then turn on S4. So therefore, VA0 is equal to minus VDC by 2. If minus VR of t is greater than VC of t, then turn on S3. So therefore, VB0 is equal to VDC by 2. Similarly, if minus VR of t is less than VC of t, then turn on S2. So therefore, VB0 is equal to minus VDC by 2. So these are the conditions you need to follow in order to do the switching process. So this is the conditions that you need to follow in order to do the switching process. So based on this, try to plot the VA0 and also try to plot the VB0. So therefore VAB is nothing but VA0 minus VB0, and also you can even plot the VAB. So whenever the VR of t is greater than VC of t, turn on the S1. So V0 is equal to plus VDC by 2. If VR of t is less than VC of t, means turn on S4. So therefore we are going to get V0 is equal to minus VDC by 2. If minus VR of t is greater than VC of t, means turn on S3. So therefore VB0 is equal to plus VDC by 2. If minus VR of t is less than VC of t, means turn on S2. So VB0 is equal to minus VDC by 2. So based on this basic principles, try to plot the VA0, VB0. So VAB is equal to VA0 minus VB0. So we are going to get the graph. So the graph that I have already shown you. So based on these conditions, try to plot the VA0, VB0 and also VAB. So we are going to get from 0 to pi only one polarity of pulse we are going to get in the output voltage or the line voltage. So we can say this is said to be unipolar. For carrier signal, I have already told you we are going to use the triangular waveform, which is VC of t. As a reference signal, we are going to use the sinusoidal waveform of VR of t. So VR of t is equal to Vm sin omega t. So minus VR of t is equal to minus Vm sin omega t. So if you apply the basic principle as we did in the bipolar, so the average value of this pole voltage V0 is equal to M into peak value is VDC by 2 into sin omega t. Similarly, the average value of the pole voltage VB0 is equal to M into peak value is VDC by 2 is a phase difference of pi sin of omega t minus pi. Whereas VAB, the average value of the line voltage VAB is equal to M into the peak value is VDC into sin omega t. So if you want to find what is the peak value of the fundamental component of the average value of this pole voltage is equal to peak value M VDC by 2. Similarly, if you want to find what is the peak value of the line voltage, average value is equal to M into VDC, which is this one. So as I have already shown in the graph, so here let me assume I want to write the expression of this VB0. See, I want to write the expression of VB0. See, the expression is here. I have already told you it is going to satisfy all the signals VA0, VB0 and VC0 are going to satisfy the basic property, which is they are basically having the one of the basic properties. They are odd function, off wave symmetry and also quarter wave symmetry. So therefore A0 is equal to 0, AN is equal to 0 and BN is not equal to 0 only for odd harmonics. So therefore sigma n is equal to 135 up to infinity Bn sin n omega t. So Bn is equal to, I have already told you, 4 into the peak value is VDC by 2 by n pi. So initially there is a positive pulse, so positive 1 minus. So it is going from high to low, so minus 2 cos n alpha 1. Again going from minus to plus means plus 2 cos n alpha 2. Again going from plus to minus means minus 2 cos n alpha 3. Again going from minus to plus means plus 2 cos n alpha 4. So these are the Fourier series coefficients that we are going to get. So let me assume that the Fourier series coefficient initial value I want, which is 0.92 VDC by pi. Whereas I want the third harmonic to be 0, fifth harmonic to be 0 and seventh harmonic to be 0. So based on these conditions, we are going to get 4 equations with 4 unknowns. We can easily figure out the alpha 1, alpha 2, alpha 3, alpha 4. So with the help of this alpha 1, alpha 2, alpha 3 and alpha 4, we can say that P1 is equal to 0.92 VDC by pi and third harmonic is equal to 0, fifth harmonic is equal to 0 and seventh harmonic is equal to 0. So with the help of this process, we are going to get a PHP which is less than, it is lies between 0 to 5 percentage in the output voltage. And always the carrier signal in the bipolar is always lesser than the carrier signal in the unipolar. It's a very important point. So we can say that the carrier signal in the unipolar is always greater than the carrier signal in the bipolar. So because of this reason only, we are going to get more number of pulses in half of the cycle in the output voltage. So more number of pulses we are going to get in the unipolar when compared to bipolar. In the unipolar we are going to get more number of pulses in the output in half of the cycle. So because of that we can say that the carrier signal used in the unipolar is always greater than the carrier signal used in the bipolar. And I have already told you one of the basic important principle, the fundamental frequency of the pole voltages V0 and VB0 is equal to the fundamental frequency of the line voltage. All these things are going to be equal to the reference signal. This is a very important point I have already told you. So if you change the reference signal frequency, the frequency of this pole voltage and the frequency of the line voltage, the fundamental frequency are going to change. It is equal to reference signal. Whereas if you increase the carrier signal frequency, the number of pulses in a given half cycle are going to get increased. That is the only thing that you need to understand. So always in a unipolar, we are going to get more number of pulses in a given half cycle. So therefore the carrier signal in the unipolar is always greater than the carrier signal in the bipolar. See, now we are going to study the one more important basic concept, which is the sinusoidal PWM. Means I am going to use the reference signal as sine wave and the carrier signal as the triangular wave. So based on this condition, I am going to give you two important cases which are very much useful in the competitive examination. So I am going to give you two important cases for this sinusoidal PWM. So reference signal is nothing but the reference signal we are going to use the sine wave and the carrier signal we are going to use the triangular waveform. So this is a case 1 I am going to give you. The case 1 is here. You can see clearly the reference signal is nothing but here this is the sine wave and the carrier signal is nothing but this is a triangular waveform. So you can see clearly initially the peak value is present. So initially the reference signal value is 0, whereas the initial value of the carrier signal is peak value. This is a very important point. Case 1 is the initial value of the reference signal is 0 and the initial value of the carrier signal is peak value. So then I am going to draw the graph like this. So this is the reference signal. This is the reference signal from 0 to pi to 2 pi. So here it is going to have peak value. So like this we are going to get. So this is the thing that we are going to get. So this is the graph we are going to get. So there are 3 pulses in the positive half cycle and the 3 pulses we are going to get in the negative half cycle also. So now I have already told you whenever the reference signal is greater than the carrier signal, then only we have to generate the triggering pulse. So output voltage is equal to plus VDC. Here also the reference signal is greater than carrier signal. So we are going to generate a output pulse of plus VDC. Here also the reference signal is greater than the carrier signal. So we are going to generate a pulse of output voltage of plus VDC. Here also the reference signal is greater than the carrier signal. So therefore we are going to generate a negative pulse here because in the negative pulse. So minus VDC. Here also the reference signal is greater than the magnitude value. Only the magnitude value is greater than this one triangular waveform. So therefore again we are going to generate a pulse of minus VDC. Here also the reference signal is greater than the in terms of magnitude is greater than the triangular waveform. So here also we are going to generate a pulse of minus VDC. So you can see clearly, so this is the nature of the output we are going to get. It is of unipolar because in a 0 to pi only one type of pulse is present. So it is basically a unipolar. So now I am going to do the analysis of this one. So now 0 to pi we get. So in 0 to pi we can see clearly that 3 into Tc is equal to Tr by 2. So 3 into Tc is equal to Tr by 2 because so each carrier signal time period is Tc. So there are 3 pulses. So 1, 2 and 3 pulses. So 3 into Tc is equal to half of the reference signal. So Tr by 2. So 3 into Tc is equal to Tr by 2. So if we do the manipulation, we are going to get, because Fc is equal to 1 by Tc and Fr is equal to 1 by Tr. So by that we are going to get 3 is equal to Fc by 2 Fr. So 3 is nothing but N. So n is equal to Fc by 2F4. This is called as the general equation, which is n is called as the number of output pulses in half cycle, and Fc is called as the carrier frequency, and F4 is called as the reference frequency. It's a very important point. N is equal to Fc by 2Fr, where Fc is called as the frequency of the carrier signal, and Fr is called as the frequency of the reference signal, and N is the number of pulses in the output voltage in a given half cycle that we are going to get. Only this is a condition only when, this is the equation only when the initial value of the reference signal is 0 and the initial value of the carrier signal is peak value. So now we are going to study the second case. So now we are going to study the another case. The another case is here. Now here same thing again, we are going to take the reference signal as sine wave and the carrier signal as the triangular waveform. But the only difference is the initial value of the reference signal is 0 and the initial value of the triangular waveform is also 0. That is the important point that you need to note down. Then what is the equation that we are going to get? You can see clearly. So now simply now we are going to take 4 pulses of carrier signal. 1 pulse, 2 pulse, 3 pulse and 4 pulse. And here also 4 pulse. 1, 2, 3, 4. 4 pulse we are going to consider. So therefore now what is going to happen? So now we have to see what is the nature of these things. So there are 4 pulses. So I have already told you, whenever the reference signal is greater than carrier signal, you have to generate a plus VDC. So plus VDC. Here also the carrier signal is, the reference signal is greater than the carrier signal. So therefore we are going to trigger. So therefore we are going to get plus VDC. Here also we are going to get a plus VDC. Whereas here the reference signal is greater than the carrier signal. So we are going to trigger the S3, S4. So therefore V0 is equal to minus VDC. Again here also at this point and this point also, in this range also, simply at this range and this range we can simply say that here the reference, so only on these regions the reference signal is greater than the carrier signal. So therefore we have to trigger S3, S4. So therefore V0 is equal to minus VDC. So simply we can say that in the positive pulse, wherever the reference signal is greater than carrier signal, in that pulse only we have to trigger the S1, S2. So therefore V0 is equal to plus VDC. Whereas here whenever the reference signal is greater than carrier signal in a negative pulse, then we can simply only the magnitude part, then we can say that trigger the S3, S4. So therefore we are going to get V0 is equal to minus VDC. So now you can see clearly there are only 3 pulses we are going to get. Only 3 pulses we are going to get in the output. So only 3 pulses we are going to get, pulse 1, pulse 2 and pulse 3. In a given half cycle we are going to get only 3 pulses. So now we are going to do the analysis in 0 to pi we get, because there are 4 triangular pulses in a given half period. So therefore 4 into Tc is equal to R by 2. So 4 is equal to here, because Fc is equal to 1 by Tc and Fr is equal to 1 by Fr. So we are going to get 4 is equal to Fc by 2 Fr. So simply we can say that here we can write n plus 1 is equal to Fc by 2 Fr. So n is equal to Fc by 2 Fr minus 1. It's a very important equation. But in the previous case, n is equal to Fc by 2 Fr. But here n is equal to Fc by 2 Fr minus 1. So in the first case, the initial value of the reference signal is 0, whereas the initial value of the reference signal is peak value. Whereas here, the second case, the initial value of the reference signal and the carrier signal both are 0. So this is the thing that we need to be careful. So therefore, n is called as the number of pulses in the output voltage in a given half cycle, and Fc is called as the carrier frequency, and Fr is called as a reference frequency. So n is called as the number of output pulses in half cycle. So this is a very important thing that you need to always be careful to remember. Always Fc is always greater than the Fr. Then only we can generate the pulses in the output. And always the peak value of the reference signal is always lesser than the peak value of the carrier signal. Then only we are going to get the pulses. So now we are going to discuss about the 3-phase inverter. So in the 3-phase inverter, we are going to study the 2 important modes of operation. One is the 180-degree mode of operation and the other is the 120-degree mode of operation. So 3-phase inverter means basically we are going to convert a DC supply into an 3-phase AC supply. That is the meaning of this 3-phase inverter. So we are going to convert this fixed DC into a AC we are going to convert. So therefore here this is a circuit diagram of this 3-phase inverter. So this overall supply voltage is VDC because these two are in series. So if we add these two things, the overall supply voltage will be equal to VDC. So the transistors T1, T3, T5, T4, T6 and T2. So this is the combination of the thyristor we are going to use with a parallel combination of the diodes. So T1, T3, T5, T4, T6 and T2. So at each and every way we are going to take one wire. So at this each points we are going to take one wire and we are going to connect to this three-phase balance load. Either it can be star connection or either it can be a delta connection, three-phase. So now in this case I am going to use a three-phase balance star connected load across these three terminals. So let me assume the current in the thyristor T1 is T1. So therefore IT1 is called as the current in the thyristor T1. See, whenever the loads are pure resistive loads, the free wheel diodes are not going to conduct. So for these pure resistive loads, the free wheel diodes are not going to get conduct. Only thyristors are going to get conduct. So we are going to study only for the resistor loads of balanced star connection or balanced delta connection. So this is the star connection. Resistor and resistor. These three are covered in a star function. So balanced star connected load with the terminals A, B and C and the neutral point is N. So this is the connection of this balanced star connected load we are going to get connected. We are going to analyze two important modes of operation. One is the 180-degree mode of operation and the other is the 120-degree mode of operation. So first thing is we are going to analyze the 180-degree mode of operation. So we are going to analyze the 180-degree mode of operation. So what is the control scheme or the switching of thyristors? So you can see clearly 180-degree mode of operation indicates that each thyristor is going to conduct for 180 degree. That is the meaning of this one. So each thyristor is going to connect for 180 degree mode. So therefore, in the first leg there are two switches T1 and T4. So T1 is going to connect from 0 to 180 degree and T4 is going to connect from 180 to 360. So you can see clearly T1 and T4 each are going to connect for 180 degree range. Similarly, in the second leg there are T3 and T6. So with a phase shift of 120. So with the phase shift of 120 from here, each thyristor is going to connect for 180 degree mode. So therefore T3 is going to connect from 120 to 300 and T6 is going to connect from 300 to 120. So in this range you can see clearly each thyristor is going to connect for 180 degree range. Similarly, in the third leg there are T5 and T2 thyristors. So after a phase shift of 240 from origin, so from 240 to 60 degree, T5 is going to connect and the remaining range 60 to 240, T2 is going to connect. So you can see clearly that each thyristor is going to connect for only 180 degree range. So this is the control scheme of this 180 degree mode of operation. So I have already told you each switch is going to connect for only 180 degree duration. So each switch is going to connect for 180 degree duration. So at any instant of time, three switches are connecting. So you can see clearly from the control scheme only at any point of time, three switches are going to connect. So at any instant of time, three switches are going to connect. So that is the meaning of this control scheme. So from the control scheme we can see that at any instant of time, three switches are going to connect. So each from each leg. So therefore overall three switches are going to connect from each leg. So at any instant of time, three switches are going to get connected. And here VAN, VBN and VCN are called as the phase voltages. So these are the line to neutral. It's called as the phase voltages. Whereas line to line voltage means VAB, VBC and VC are called as the line voltages. Whereas the pole voltages VA0, VB0 and VC0 is called as the pole voltages. So the phase voltages are the line to neutral voltage, which is VAN, VBN and VCN. Whereas the line voltages are the VAB, VBC and VCA. Whereas the pole voltages are the VA0, VB0 and VC0. So 0 is the point which is in between the two DC sources. So 0 is the point. So these are called as the pole voltages. So if you know the phase voltages, you can easily get the line voltages also. So the line voltage VAB is equal to VAN minus VBN. So line voltage VAB is equal to VAN minus VBN. VBC is equal to VBN minus VCN. VCA is equal to VCN minus VAN. So you can easily get the line voltage from the phase voltages. So VAB is equal to VAN minus VBN. VBC is equal to VBN minus VCN, VCA is equal to VCN minus VAN. So from this you can easily get the line voltage from the phase voltages. Now we are going to draw the phase voltages and also the line voltages. The phase voltages which we are going to draw, which is VAN, VBN and VCN. And then we are going to find what is the line voltage VAB, which is VAN minus VBN. So these are the graphs that we are going to draw. So from 0 to 60 degree, you can clearly see from the control scheme diagram. So you can see from the control scheme diagram that T1, T6 and T5 are going to conduct. So if you on these three switches and if you analyze the circuit, then we are going to get the phase voltages, which is VAN as VDC by 3, VBN as minus 2 VDC by 3 and VCN is equal to VDC by 3. So with the help of this, you can plot on the graphs. Similarly, from 60 degree to 120 degree, so you can see clearly from the control scheme diagram, which is T1, T6 and T2 are going to conduct. So if you close these switches from the circuit diagram and if you analyze the circuit, then we are going to get the phase voltages, which is 2 VDC by 3, minus VDC by 3 and minus VDC by 3. So therefore, VAN as plus 2 VDC by 3 and VBN as minus VDC by 3 and VCN as minus VDC by 3. So these are the voltages that you are going to get and you can easily draw on the graph. And now from 120 degree to 180 degree mode, you can see clearly from the control scheme diagram, which is T1, T3 and T2 are going to conduct. So if you close these switches and if you analyze the circuit diagram, we are going to get VN as plus VDC by 3, VBN as plus VDC by 3 and VCN as minus 2 VDC by 3. So these are the voltages that you are going to get. Similarly, from 122 to 180 to 240. So from 180 to 240, you can see clearly T4, T3 and T2 are going to connect. So if you close these three switches and if you analyze the circuit, then we are going to get VAN as minus VDC by 3, VBN as plus 2 VDC by 3 and VCN as minus VDC by 3. So these are the voltages that you are going to get and you can usually plot on the graph. Similarly, from 240 degree to 300 degree, you can see clearly from the control scheme diagram that T4, T3 and T5 are going to get conduct. So if you close these switches and if you analyze the circuit diagram, then you are going to get VAN as minus 2 VDC by 3, VBN as plus VDC by 3 and VCN as plus VDC by 3. So these are the voltages that you are going to get and you can easily draw on the graph. Similarly, from 300 to 360 degree, you can see clearly from the control scheme diagram that T4, T6 and T5 are going to get conduct. So if you close these three switches and if you analyze the circuit, then we are going to get, which is VAN as minus VDC by 3 and VBN as minus 2, VBN as minus VDC by 3 and VCN as plus 2 VDC by 3. So you can see clearly, so finally we are going to draw the graph. So you can see clearly that these are the graphs that you are going to get. So these are the graphs that you are going to get. So easy way to remember is, if you shift the VN by 120 degree, you are going to get VBN. And if you shift the VN by 240 degree, then you are going to get the VCN. So if you remember this graph, just go for shift of 120, you are going to get VBN. Just give a shift of 240, you are going to get the VCN. This is the easy way to remember. So the easy way to remember is here, plus VDC by 3, plus 2 VDC by 3, plus VDC by 3, minus VDC by 3, minus 2 VDC by 3 and minus VDC by 3. So for every 60 degree. So this is the way that you are going to remember this circuit, remember this graph. So if you want the line voltage VAB, which is VAN minus VBN, so VAB is equal to VAN minus VBN. The only graph which I am going to draw the line voltage is VAB, so therefore VAN minus VBN. So if you do the subtraction of these two graphs, then finally we are going to get the VAB. So this is the graph that you are going to get, which is VAB. So VAB is called as the line voltage. So you can see clearly that the phase voltages are the stepped square waveform, whereas the line voltage is a cos square waveform. So this is the graph that you are going to get. And in the examinations, they are going to ask you what is the peak to peak value of phase voltages. The positive peak value is 2 VDC by 3 and negative peak value is minus 2 VDC by 3. So if this subtraction, we are going to get 4 VDC by 3 is the peak to peak value of the phase voltages, whereas for the line voltage, the positive peak value is plus VDC and the negative peak value is minus VDC. So if it is subtraction of these two things, we are going to get 2 VDC. So simply I can say that the peak to peak value of the phase voltage is 4 VDC by 3, whereas the peak to peak voltage of a line voltage is 2 VDC. So this is the thing that you need to easily remember. So now the peak to peak value of the phase voltage is 4 VDC by 3 and the peak to peak value of the line voltage, which is 2 VDC. And the waveform of the phase voltage is in the shape of a step square waveform, whereas the line voltage is in the shape of the cos square waveform. We are going to find what is the value of the phase voltage RMS value. So let me take any phase voltage. So I am going to take the phase voltage VAN and I am going to find what is the value of the RMS. So phase voltage RMS value. So for the phase voltage VAN, I am going to find its RMS value. So therefore here V phase RMS value is equal to under root over 1 by. So for only for pi degree I am going to do this simplification. So 1 by pi, which is VDC by 3 whole square into 60 degree plus 2 VDC by 3 whole square into 60 degree plus VDC by 3 whole square into 60 degree. So if you solve this one, we are going to get the V phase RMS value is equal to root 2 by 3 into VDC. So this is the phase voltage RMS value, which is root 2 by 3 into VDC. And similarly, I want to find the RMS value of the line voltage. So let me take the line voltage VAB and I want to find what is the RMS value of this line voltage. So VAB RMS value is equal to, which is line voltage RMS value. So if you try to figure out the line voltage RMS value, which is VL RMS is equal to under root over 1 by pi VDC whole square into 120 degree. So this is the case we have to go for this one. So if you do this one, the line voltage RMS value is equal to under root over 2 by 3 into VDC. So I recommend you to remember only this line voltage RMS value. So therefore, the line voltage RMS value is equal to under root over 2 by 3 into VDC. So therefore, we can simply say that the line voltage RMS value is equal to root 3 into phase voltage RMS value. So this is the relation between the RMS value of the line voltage and the RMS value of the phase voltage. So if you remember the RMS value of the line voltage, you can substitute here, and if you do simplification, simply we can get the RMS value of the phase voltage. So the line voltage RMS value is equal to under root over 2 by 3 into VDC. So therefore, the line voltage RMS value is equal to root 3 into V phase RMS. So now I am going to draw what is the nature of the thyristor current T1. So IT1 is T1 is going to conduct only from 0 degree to 180 degree. So from 0 degree to 180 degree, T1 is going to get conduct. So after that T1 is off, so therefore current is equal to 0. So whenever the T1 thyristor is on, then what is the IT1? So IT1 is equal to phase voltage VAN by R. Therefore, thyristor T1 is equal to phase voltage VAN by R. So in this region, what is the value of the phase voltage? Then go for division of that thing. So already I told you from 0 to 60 degree, the phase voltage of VN is equal to VDC by 3. So if you want the current divided by R, so VDC by 3R. Similarly, from 60 degree to 120 degree, the phase voltage VAN from 60 degree to 120 degree, I can say clearly that the phase voltage VAN is plus 2 VDC by 3. So if you want the current which is divided by R, so we are going to get 2 VDC by 3R. Similarly, from 120 degree to 180 degree, the phase voltage VAN is VDC by 3. So if you want the thyristor current IT1, which is VDC by 3R. So this is the nature of the thyristor current, which is IT1. So now we are going to find what is the RMS value of this thyristor current we are going to figure out. So the RMS value of thyristor current T1, so IT1 RMS is called under root over 1 by 2 pi. So 1 by 2 pi into VDC whole square. So VDC by 3R whole square. So VDC by 3R whole square into 60 degree plus 2 VDC by 3R whole square into 60 degree plus VDC by 3R whole square into 60 degree, or simply we can say which is VDC by 3R whole square into 150 degree plus 2 VDC by 3R whole square into 60 degree. So if you do this one, finally we are going to get the RMS value of thyristor T1 current, which is VDC by 3R. So IT1 RMS is equal to VDC by 3R. So this is the RMS value, the resistor current P1. So IT1 RMS is equal to VDC by 3R. So if you want to know how much amount of average power consumed by this three-phase load, therefore the average power consumed by this three-phase load P0 is equal to 3 into V phase RMS square by R. So the V phase RMS whole square by R. Simply we can say that V phase RMS whole square by R means only one phase. There are three phases into 3. The average power consumed by this load is equal to 3 into V phase RMS whole square by R is equal to, or simply we can also write, which is I phase RMS whole square into R. So I phase RMS whole square into R, or simply 3 into V phase RMS whole square by R. So you can go for any of this formula. So for a star connected load, I have already told you, for a star connected load, we have to remember the line voltage RMS value. I have already told you. The line voltage RMS value is equal to under root of 2 by 3 into VDC. So you know the relation between the line voltage and phase voltage RMS value. The line voltage RMS is equal to root 3 into V phase RMS. So if you substitute that equation and if you solve this one, we are going to get V phase RMS is equal to root 2 by 3 into VDC. So, and the average power consumed by the load is 3 into V phase RMS whole square by R. So if you know line voltage, substitute here, we are going to get the phase voltage. So you can substitute phase voltage here, and if you do simplification, we are going to get the average power consumed by this load. Suppose for delta connected load, suppose if the load is delta connected, then how you are going to figure out? So try to convert this delta load into a star load, and then apply these formulas. Then you are going to get the average power consumed by this load. So I have told you, try to convert the delta load into star load and apply these formulas. Then you are going to get the solution. Otherwise you can also correctly use a delta connected load. I have already told you, always do remember this line voltage value, because in delta connected load, the line voltage is equal to phase voltage into delta connected load. The line voltage is equal to phase voltage. So they are always both are equal. So the line voltage RMS is equal to phase voltage RMS is equal to root over 2 by 3 into VDC. So apply this value, which is P0 is equal to 3 into V phase RMS squared by R. So you can apply this formula to get the result. So I have already told you, either we convert the delta load into star load and apply these formulas. Otherwise, use this formula, which is the line voltage RMS is equal to phase voltage RMS value. Line voltage RMS value just now we have figured out. So keep here, and if you do simplification, you are going to get the result. Either you go by this method or either you go by this method. Both are going to give the same result. But the formula is same, which is 3 V phase RMS whole square by R. But here, 3 phase RMS, this V phase RMS value is equal to the line voltage RMS value. So now, we are, as I have already told you, the phase voltages are the stepped square waveform. So now I am going to write the Fourier series expansion of this phase voltage. So it's equal to VAN of T is equal to sigma n is equal to 135 up to infinity 4 VDC by 3 pi n into 1 plus cos n pi by 3 into sin n omega t. So as I already told you, this phase voltage and the line voltage are both odd functions, half wave symmetry and quarter wave symmetry. So because of that, the even elements are going to get absolutely, odd elements are going to present sigma n is equal to 135 up to infinity 4 VDC by 3 pi n into 1 plus cos n pi by 3 into sin n omega t. So here, if you substitute, here n is equal to 3. What is going to happen? So cos pi is nothing but you are going to get minus 1. So minus 1 and plus 1 is 0. So therefore, all the 3 n odd harmonics are going to get absent. So simply we can say that all the 3 n odd harmonics are going to get absent. So for remaining or other, see, but suppose cos pi by 3 means, simply we can say that cos pi by 3 is cos 60 is equal to half. So cos 60 is equal to half. Half plus 1 is t by 2. So you are going to get in this format. So simply, finally, sigma n is equal to 6k plus or minus 1 into infinity 2 VDC by n pi into sin n omega t. Where k is equal to 0, 1, 2. Hence we simply say that n odd harmonics are going to get absent. So simply this equation is going to simplify to this expression sigma n is equal to 6k plus or minus 1 to infinity 2 VDC by pi n into sin n omega t. The k is from 0, 1 to goes on to infinity. So I can simply say that all the 3 n odd harmonics are going to absent in this phase voltage. So I want to find what is the value of the fundamental component RMS value in this voltage. So therefore, the fundamental component is n is equal to 1. So if you substitute n is equal to 1, and if you do the division by root 2, so the RMS value of the fundamental component of the line of this phase voltage is root 2 VDC by 5. Suppose if you want to find what is the overall RMS value, I already told you the phase voltage RMS value is equal to root 2 by 3 into VDC. So this is the RMS value of the phase voltage, is root 2 by 3 VN. So if I want to find what is the distortion factor, it's the ratio of the RMS value of the fundamental component of the voltage by the overall voltage RMS value. So G is equal to distortion factor, it's the ratio of the RMS value of the fundamental component of the phase voltage by RMS value of the overall phase voltage. So you know this both things, do a division, we are going to get 3 by 5. So PhD is equal to under root over 1 by G whole square minus 1. So G value, if you substitute and if you do simplification, we are going to get 0.31. So this is the distortion factor and the PhD for this phase voltage. Similarly, I am going to write the line voltage expression. So line voltage expression, as it is a process pure waveform, and I am going to get like this. Sigma m is equal to 135 to infinity 4 VDC by n pi sin n pi by 3 into sin n pi by 2 into sin of n omega naught t plus n pi by 6. So this is the I am going to take. So sigma m is equal to 135 to infinity 4 VDC by n pi into sin n pi by 3 into sin n pi by 2 into sin of n omega naught t plus n pi by 6. So you can see clearly if you substitute n is equal to 3, here again it is going to become 0. So I can already tell that here also the 3 and odd elements are going to get absent. So 3 and odd elements are going to absent in the both the phase voltage and also in the line voltage. So this equation simply is going to simplify to sigma m is equal to 6 plus or minus 1 into the 4 VDC by n pi sin n pi by 3 into sin n pi by 2 into sin of n omega t plus n pi by 6. So in the k is equal to 0, 1 to up to infinity. Yes, this equation is not going to hold any real odd elements. So now if I find what is the fundamental component of the line voltage RMS value is equal to, if you substitute n is equal to 1 and if you do the division by root 2, we are going to get root 6 by pi into VDC. So now here if you want to find what is the RMS value of the line voltage, first now we have to look at under root over 2 by 3 into VDC. So therefore the distortion factor of this line voltage, is equal to RMS value of the fundamental component line voltage by RMS value of the line voltage. If you know both the things, to the division we are going to get 3 by 5. So therefore PhD is equal to under root over 1 by G whole square minus 1. So if you substitute here, you are going to get 0 by 31. So you can see clearly the distortion factor and the PhD both are same for both the line voltage and also the phase voltage. Suppose if you want to know what is the expression of this pole voltage, I am going to take here VA0. So VA0 means here whenever the T1 is conducting, VA0 is equal to VDC by 2. So whenever the T1 is connecting, so T1 is connecting from 0 to 180 degree, so therefore VA0 is equal to plus VDC by 2. Whenever from 182 to 360 degree, T4 is conducting, so therefore VA0 is equal to minus VDC by 2. So this is the graph that we are going to get. So VA0. So VA0 of T is equal to sigma n is equal to 135 up to infinity 4 into the peak value is VDC by 2 by n pi sin n omega naught t. So this is the expression that we are going to get finally, which is sigma n is equal to 135 up to infinity VDC by n pi into sin n omega naught t. So except R load. What is going to happen? So for R load I have already told you the free wheel diodes are not conducting, only the thyristor is going to conduct for 180 degree range. So except R load, the conduction angle of each thyristor is equal to pi minus phi 1, as the conduction angle of each diode is equal to phi 1. So this is the way we need to understand. So for except R load, the conduction angle of each thyristor is equal to pi minus phi 1, as the conduction angle of each diode is equal to phi 1. Phi 1 is called as the power factor of the load, so power factor angle of the load. So phi 1 is called as the power factor angle of the load. So 3 and hard harmonics are absent in phase voltage and also in the line voltage. I already told you always 3 and hard harmonics are going to always absent in both the phase voltage and also line voltage. Whereas 3 and hard harmonics are present in the pole voltage, yes, this you can already see. So I can say that 3 and hard harmonics are absent in phase voltage and also line voltage, but they are present in the pole voltage. So VAN and VBN have odd harmonics, excluding PN harmonics. VAN have odd harmonics, including PN harmonics. Means here simply I am simply just going to report. So phase voltage and line voltage are basically not going to have any PN harmonics. PN are odd harmonics. Whereas the pole voltage is going to have the PN harmonics. So simply we can say that VAN and VBN, the line voltage, the phase voltage and the line voltage are going to have odd harmonics except 3N odd harmonics. Means excluding means removing. So remove 3N odd harmonics. Whereas V0 is going to have odd harmonics including the 3N harmonics. So simply I can say that the phase voltage and line voltage are not going to have any 3N odd harmonics. Whereas the pole voltage is going to have even the 3N odd harmonics. That is the meaning of this sentence. Now we are going to study the 120 degree mode of operation. So before we study these graphs, let us first do some more analysis of this 120 degree mode of operation. So now we are going to do the analysis of this 120 degree mode of operation. So you can see clearly that out of 180, from 0 to 180, each thyristor is going to connect for only 120 degree. So from 0 to 180 degree, each thyristor is going to connect for only 120 degree. That is called as the 120 degree mode of operation. Means each thyristor is going to connect for only 120 degree duration. In the first leg, there are two thyristors T1 and T4. So from 0 to 180, T1 is going to connect only for 120. The remaining range is off. Similarly, T4 is going to connect from 180 from duration of 180 to 360, it is going to connect only for 120. So therefore 180 to 300, and here it is going to connect. So the remaining range it is going to get off. Similarly, if you do a phase shift of 180 degree, so here in the second leg there are T3 and T6. So T3 is going to connect for in the range of 180, it is going to connect for only 120. And from 300, T6 is going to connect for only 120, and the remaining range is off. So if you give a phase shift of 240, so therefore from here, the third leg there are two thyristors T5 and T2. So T5 is going to connect for only 120, and the remaining range is off. Similarly, T2 is connect for only 120, and the remaining range is off. So I can simply say that, so from 0 to 180 degree, only 0 to 180 degree, plus only 120 degree mode it is going to connect, and the remaining range will be off. That is the meaning of this one. So this is basically the control scheme of the switching of these thyristors. So each switch is going to connect for only 120 degree duration. So each switch is going to connect for only 120 degree duration. So at any instant of time, two switches are connecting. So at any instant of time, two switches are going to connect. So here, each switch is going to connect for only 120 degree range, and also at any time only two thyristors are going to get connected. The basic agenda of this 180 degree mode is, because in 180 degree, due to a small amount of inductance, a small amount of source inductance, there may be possible of short circuiting of one leg. So T1 and T4 both may be connecting at the same instant of time. So because of that, there will be a short circuit in the leg. So because of that, there will be a short circuit of the supply. So because of that, only we are going to prefer the 180 degree mode of operation. That problem is absent in this 180 degree mode of operation. The phase voltages are the VAN, VBN and VCN are called as the phase voltages, and as the line voltages are the VAB, VBC and VC are called as line voltages, and the pole voltages are the VA0, VB0 and VC0 are called as the pole voltages. So line voltage is a subtraction of the phase voltage. So VAB is equal to VAN minus VBN, VBC is equal to VBN minus VCN, so VCA is equal to VCN minus VAN. So this is the line voltage in terms of the phase voltages. So now I am going to draw the graph of the phase voltage and also the line voltage. So phase voltages which I am going to draw, which is VN, VBN and VCN, and also I am going to draw the line voltages which is VAB. So you can see clearly from 0 to 60 degree. So from 0 to 60 degree, only T1 and T6 are going to connect. Only T1 and T6 are going to connect. So I can say that from the, if you on the T1 and T6 and if you analyze the circuit, then finally we are going to get VNS plus VDC by 2 and VBNS minus VDC by 2 and VCNS 0. So these are the things that we are going to get. So therefore this is the diagram we are going to get. Similarly, from 60 degree to 180 degree, if you see from the control scheme, T1 and T2 are going to connect, So if you have the T1 and T2, if you analyze the circuit, we are going to get DAN as plus VDC by 2, VBN as 0, and VCN as minus VDC by 2. Similarly, from 130 degree to 180 degree, if you see from control scheme, you are going to get P2 and P3 are going to connect. So therefore, if you analyze the circuit by only the P2 and P3, we will get VN is equal to 0, and VBN is equal to plus VDC by 2, and VCN is equal to minus VDC by 2. Similarly, from 180 to 240, you can see clearly for every 60 degree we are going to analyze. So from 180 to 240, you can say from the control scheme diagram, T4, T3 are going to connect. So Vn is equal to minus VDC by 2, Vbn is equal to plus VDC by 2, and Vcn is equal to 0. Similarly, from 240 to 300 degree, you can see from the control scheme diagram that T4 and T5 is going to connect. So if you have this T4 and T5, and if you analyze the circuit, we are going to get VAN as minus VDC by 2, VBN as 0, and VCN as plus VDC by 2. Similarly, from 300 to 360 degree, you can see clearly from the control scheme diagram that T6 and T5 are going to connect. So if you have this T6 and T5 and if you analyze the circuit, we are going to get VN as 0, VBN as minus VDC by 2, and VCN as plus VDC by 2. So these are the graphs that we are going to get. So if you remember only this one graph, you can easily draw the other graphs also, which is this is plus VDC by 2, plus VDC by 2, 0, minus VDC by 2, minus VDC by 2 for every 60 degree. So if you give a phase shift of 120, you are going to get PPF. If you give a phase shift of 240, you are going to get VCN. So if you remember this one graph, plus VDC by 2, plus VDC by 2, 0, minus VDC by 2, minus VDC by 2, 0. So this is the graph we have to remember for every 60 degree. So if you want the line voltage, which is the phase voltage VN minus VBN, so if it is subtraction of these two phase voltages, we are going to get the line voltage. So this is the phase voltage that we are going to get finally. So this is the phase voltage that we are going to, this is the line voltage that we are going to get from the phase voltage VAB. See, you can see clearly that the phase voltage is like a cos square waveform, whereas the line voltage is a step square waveform. And the positive peak value of the phase voltage is plus VDC by 2, and the negative peak value of the phase voltage is minus VDC by 2. So the peak to peak value is plus VDC. Whereas the line voltage, the positive peak value is plus VDC, and the negative peak value is minus VDC. So the peak to peak value is plus 2 VDC. So therefore, this is the plus 2 VDC is the peak to peak value of this line voltage. Whereas for phase voltage, the peak to peak value is VDC, whereas the line voltage, the peak to peak value is plus 2 VDC. So if you want to draw the graph for the thyristor T1, so thyristor T1 is on only from 0 to 120 degree, and the remaining range is off. So the remaining range current is will be 0. So only from 0 to 120 degree, T1 is going to get conducted. So whenever the T1 is conducting, the thyristor IT1 is equal to phase voltage VN by R. So from 0 to 60 degree, the phase voltage VN is equal to VDC by 2. So its current is VDC by 2R. Similarly, from 60 to 180 degree, the phase voltage Vn is equal to VDC by 2. So thyristor current IT1 is equal to again VDC by 2R. So this is the current that you are going to get finally. So this is the thyristor current T1. Suppose if you want to draw what is the pole voltage VA0. So VA0, see T1 is connecting only from 0 to 120 degree. So whenever the T1 is connecting, its pole voltage is equal to plus VDC by 2. So 0 to 180 degree, it is on. So therefore, we are going to get plus VDC by 2. In 120 to 180, T1 is off, T4 is off, and both are off. Its voltage is equal to 0. From 180 to 300 degree, again T4 is connecting. So whenever T4 is connecting, the pole voltage VA0 is equal to minus VDC by 2. So minus VDC by 2. Again from 300 to 360, both are off. T1 is off and T4 is off. Therefore again, its voltage is equal to 0. So now we are going to find what is the RMS value of the phase voltage. So VN RMS is equal to V phase RMS is equal to, so the RMS value of the phase voltage is equal to under root over 1 by pi VDC by 2 whole square, VDC by 2 whole square into 60 degree plus VDC by 2 whole square into 60 degree, or simply VDC by 2 whole square into 180 degree. So if you solve this one, we are going to get VDC by root 6. So V phase RMS is equal to VDC by root 6. So V phase RMS is equal to VDC by root 6. So here, if you want to find what is the RMS value of the line voltage, so VAB RMS is equal to VL RMS. So V line voltage RMS value is equal to, so you can get from this graph, which is under root over 1 by pi into 1 by pi into VDC. VDC whole square into 60 degree. VDC whole square into 60 degree plus VDC by 2 see whole square into 60 degree plus VDC by 2 whole square into 120 degree. So if you solve this one, we are going to get VDC by root 2. So line voltage RMS value is equal to VDC by root 2. So therefore, the line voltage RMS value is equal to VDC by root 2. So this is the thing that you need to remember. If you remember this one, you can easily go for the other things also. So the line voltage RMS value is equal to VDC by root 2. So the line voltage RMS value is equal to VDC by root 2. So the line voltage RMS is equal to root 3 into V phase RMS. So if you remember this one equation, you substitute here, we are going to get the phase voltage RMS value also. So line voltage RMS is equal to VDC by root 2. So if you want to find what is the RMS value of the thyristor current, so you can see clearly from the graph, VDC by 2 or under root 2 or 120 degree by 360 degree. So if you solve this one, we are going to get VDC by 2R into root 3. So this is the value of the thyristor current RMS value. I already told you for star connected load. For star connected load, the line voltage RMS value is equal to VDC by root 2, and the phase voltage RMS value is we have VDC by root 3. So if you remember this line voltage, simply we can keep in terms of the basic relation VLM RMS is equal to root 3 into V phase RMS, then we get the V phase. So the average power consumed by the load is equal to 3 into V phase RMS whole square by R. So then we substitute this value here, and if you do simplification, we are going to get the amount of average power consumed by this load. Similarly, for delta connected load, we try to convert in terms of star connected load and apply these basic formulas. Otherwise, what we do, we keep as it is delta connected load, and then try to, in this delta connected load, the line voltage is equal to phase voltage RMS value. So therefore, the line voltage RMS is equal to phase voltage RMS is equal to VDC by root 2. So substitute here, the average power consumed by the load is equal to 3 into V phase RMS whole square by R. So V phase RMS is equal to VA RMS. So substitute here, and we get the value of the solution. So in 180 degree mode of operation, the line voltage RMS is equal to under root 2 or 2 by 3 into VDC. Whereas here, in 180 degree mode of operation, the line voltage RMS is equal to VDC by root 2. This is the only thing that you need to remember, and remembering everything is very easier. See, as I have already told you, in 180 degree mode of operation, the phase voltages are the cos square waveform, whereas the line voltage of the step square waveform. So therefore now here see, I want to write what is the expression of the phase voltage VN. So VN of T is equal to sigma n is equal to 6k plus or minus 1 infinity 2 VDC by n pi into sin n pi by 3 into sin n pi by 2 into sin of n omega naught t plus pi by 6. So k is equal to 0, 1, 2 up to infinity means this is not having any 3n odd harmonics. So 3n odd harmonics are going to purely absent for this phase voltages. So therefore, if you want to find what is the RMS value of the fundamental component of the phase voltage, so peak value substitute n is equal to 1, you are going to get the fundamental peak value divided by root 2. So we are going to get finally root over 3 by 2 into VDC by pi. So if you want to find what is the RMS value of the phase voltage, just now we have figured out which is VDC by root 6. Phase voltage is equal to VDC by root 6. So what is the distortion factor of this phase voltage, which is the RMS value of the fundamental component of the phase voltage by the RMS value of the phase voltage. So both the values we know, just do the division, we are going to get 3 by pi. So THD is equal to under root over 1 by G whole square minus 1. So G value if you substitute here, we are going to get 0.31. So now I want to write what is the expression of the line voltage. So line voltage is a step square waveform. So after writing, we are finally get 3 by 2 into sigma n is equal to 6k plus or minus 1 up to infinity 2 VDC by n pi into sin of n omega t plus n pi by 3. So if you take 3 by 2 inside, we are going to get sigma n is equal to 6k plus or minus 1 up to infinity 3 VDC by n pi into sin of n omega t plus n pi by 3. So this simply indicates that there are no 3n odd harmonics are going to get absent in this equation. So simply we can say that k is equal to 0, 1 to up to infinity means here there are no 3n odd harmonics. So 3n odd harmonics are going to be absent in both the phase voltage and also in the line voltage. So therefore we can say that it is going to be absent even in this expression also. So therefore the line voltage, the fundamental component of the line voltage RMS value is equal to, keep here n is equal to 1, keep the basic component n is equal to 1, and then if you solve this one, we are going to get simply 3 VDC by root 2 pi. The RMS value of the line voltage is VDC by root 2. Just now we have known this one. So distortion factor is equal to ratio of the RMS value of the fundamental line voltage by the RMS value of the overall line voltage. So we know both these values. Do the division, we are going to get 3 by pi. So THD is equal to 1 by G whole square minus 1. So if we substitute here, we are going to get 0.32. So this is the equation that we are going to get. So I can say simply that the line voltage and the phase voltage 3 and all harmonics are going to absent in both the 180 degree mode of operation and also in the 180 degree mode of operation. So listen carefully. In both the line voltage and also phase voltage, 3 and all harmonics are going to absent in both the 180 degree mode of operation and also in the 120 degree mode of operation. But now, if you write the pole voltage expression, so pole voltage is now a causes square waveform. So if you write the expression, we are going to get sigma n is equal to 6k plus or minus 1 up to infinity 2 VDC by n pi into sine of n pi by 3 into sine of n pi by 2 into sine of n minus 80 plus n pi by 6. So this is also not going to have any, 3 and odd harmonics. So 3 and odd harmonics are going to absent even in the pole voltage. So k is equal to 0 1 to up to infinity. So therefore 3 and harmonics are absent in phase voltage and also line voltage. 3 and harmonics are also absent in pole voltage. So this is the thing that you need to remember. So for 180 degree mode of operation, 3 and odd harmonics are absent in both the phase voltage and also line voltage, but 3 and odd harmonics are present in the pole voltage. Whereas in the 180 degree mode of operation, 3 and odd harmonics are absent in both the pole voltage and both the line voltage and also the phase voltage, but they are present, but they are also absent in this pole voltage in the 180 degree mode of operation. So listen carefully. In 180 degree mode of operation, in both the line voltage and the phase voltage, 3 and odd harmonics are absent, whereas in the pole voltage, 3 and odd harmonics are present. Whereas in the 180 degree mode of operation, the 3 and odd harmonics are absent in both the line voltage, phase voltage, and also in the pole voltage are also absent. Line voltage, phase voltage, and the pole voltage are also in each and everything. The 3 and odd harmonics are absent in the 180 degree mode of operation. So simply I can say that VAN is phase voltage and line voltage VAB has only odd harmonics excluding plain harmonics, means 3 and odd harmonics are absent in both the phase voltage and also in the line voltage. So VA not has only odd harmonics excluding 3 and harmonics, means the pole voltage is also not having any 3 and odd harmonics. So we can say simply in the phase voltage, line voltage and also pole voltage, they are not going to have any 3 and odd harmonics. Now we are going to discuss the current source inverter. So current source inverter means here I have already told you the current source inverter always the load output is always current is going to, means the current in the output load will be always constant waveform irrespective of the load elements, but the voltage waveform is going to get changed. So there are no freewheeling diodes. So freewheeling diodes are not all necessary in the current source inverter. That is the current source inverter. So I am going to analyze for the R load. So this is the circuit diagram of a current source inverter. So which is T1, T2, T3 and T4. So there is no need of freewheeling diodes. And the input we want a constant current source. So in practical we have to keep a voltage source and an inductor in series. Then only we are going to produce the input current of constant current. So this is source current IS. And this is the load we are going to keep a resistor. So this is plus or minus V0 and this is the I0. So output voltage is V0 and the output current is I0. So T1, T2, T3 and T4, the input voltage is the input voltage. So this is the circuit diagram. Now we are going to analyze this circuit diagram. So now we are going to analyze this circuit. So here you can see clearly during 0 to T by 2. So during 0 to T by 2 we are going to on T1, T2. So whenever we are going to on the T1, T2 and we are going to off the T3, T4. So from the circuit diagram we can say that here I0 is equal to IS and also V0 is equal to I0 into R, but I0 is equal to IS. So IS into R. So if you apply the KVL, we get that Vn is equal to V out. So this is the things that we are going to get. Whereas T by 2 to T, see we are going to on the T3, T4, but we are going to off T1, T2. Then, so if you analyze the circuit, we are going to get I0 is minus IS. V0 is equal to I0 into R, but I0 is equal to minus IS. So minus IS into R. So Vn is equal to minus V0. So this is the thing that we are going to get during T by 2 to T. So now based on this, we are going to draw the graphs. So now we are going to draw the graphs. From 0 to t by 2, we are going to on t1, t2. So whenever we on t1, t2 and t3, t4 is off in this period. So therefore, simply we can say that V0 is equal to plus VIN. So V0 is equal to plus VI. And also here V0 is I0 is equal to IS. So I0 is equal to IS. And also V0 is equal to I0 into R, which is IS into R. Similarly, from t by 2 to t, we can say that t3, t4 are on. So therefore, t1, t2 are off. So therefore, if you see the circuit diagram, we are going to get I0 is equal to minus IS, and also V0 is equal to I0 into R, which is minus IS into R. So this is the graph that you are going to get. So what is VIN? VIN is equal to V0 for 0 to t by 2. So whatever the V0 is also equal to VIN. Whereas from t by 2 to t0, VIN is negative of the V0. So negative of V0 means you are going to get IS into R. So this is the graph that you are going to get the input voltage, and this is the output voltage. So this is the thyristor current IT1. So this is the thyristor current IT1 is the current of the thyristor T1. So feedback diodes across the thyristors won't require because IS is always goes in one direction only. So here feedback diodes are not required across the thyristors because always IS is always in a one direction. It is always in a one unit direction. So because of this reason only, there is no need of freewheeling diodes. So feedback diodes across thyristors won't require because IS is always goes in a one direction only. So because the IS is having only one unit direction. So because of this, there is no need of feedback diodes across the thyristors. Because the IS is always having a unit direction irrespective of the load. So because of that only we can say that there is no need of feedback diodes across the thyristors. So feedback diodes across the thyristors won't require because IS is always goes in one direction only. Any load, the waveform of I0 is same, but V0 changes depending on the load. I have already told you, irrespective of the load, the output current waveform is always same. But the only thing is the output voltage is going to change based on the load elements. Vin is always positive, so power is always delivered from source to load. So you can always see that Vn is always positive. So if Vn is a positive and Is is positive, so therefore always the power is going from source to load. So always the source is going to deliver the power to the load. So Vn is always positive, so power is always delivered from source to load because Vn is always positive and Is is also always positive. So therefore their product is always positive. So therefore always the power is flowing from source to load. Also commutation for thyristors is required because there are no feedback diodes. So because of that, we need to forcefully turn off the thyristors. So therefore, here there are no feedback diodes. So therefore, the forced combination is always necessary to turn off the thyristors. So forced combination for thyristors is required because there are no feedback diodes. And now I can figure out what is the value of the RMS value of the output current. So from the graph, we can say that the RMS value of the output current is equal to IS, whereas the RMS value of the output voltage is equal to, which is IS into R, or simply it is equal to I0 RMS into R. I0 RMS is equal to IS, so IS into R. So the RMS value of the output current is IS, and the RMS value of the output voltage is equal to I0 RMS into R, which is IS into R. So you can see clearly from the graph, the conduction angle of each thyristor is pi. So each thyristor is going to conduct for only pi. So, or simply in terms of time, if you want in terms of time, which is t by 2. If you want in terms of degrees, it is pi. If you want in terms of time, it is t by 2. See, if you want to draw what is a thyristor current T1. So T1 is conducting only from 0 to t by 2. Only from 0 to t by 2, T1 is on. So whenever the T1 is on, the IT1 is equal to I0. So I0 is equal to IS in this region. So therefore, this is the thyristor current T1. So IT1 is the thyristor current in this range. So if you want to find what is the average value of the thyristor current T1, which is IS into T by 2 by T, is IS by 2. So if you want to find what is the RMS value of the thyristor current T1, which is IS into under root over T by 2 by T, which is IS by root 2. So now I want to write the expressions of the Fourier series. As I0 is a fundamental, or you can say it is a periodic signal. So I0 of t is equal to sigma n is equal to 135 to infinity 4 into peak value is is by n pi into sin n omega naught t. So this is the I0 of t we are going to get. Similarly, V naught of t is equal to sigma n is equal to 135 up to infinity 4 into the peak value is is into r by n pi into sin n omega naught t. So this is the we are going to get the output expression and the output current and the output voltage. So I want to find what is the RMS value of the fundamental component of the output current. The substitute is equal to 1, we are going to get 4 is by pi by root 2. So we are going to get this expression. If you want to find what is the RMS value of the output current, which is equal to IS. So therefore, the maximum value of the fundamental component of the output current is just substitute is equal to 1. We are going to get 4 is by pi. So what is the value of G? G is the ratio of the RMS value of the fundamental component of the output current by RMS value of the overall output current. So we know both the things. So if we substitute, we are going to get 2 into root 2 by pi. So if you want THD is equal to root over 1 by G whole square minus 1, if you substitute G here and the Fourier simplification, we are going to get 0.48. See, now I want to draw what is the nature of the fundamental component of the thyristor current. See, the thyristor T1 is connecting only from 0 to T by 2. So only in this range, whatever the current output current is equal to thyristor current. So after that it is absent, it is not connecting as 0. So whatever the fundamental component in 0 to T by 2 of phi naught will be same as IT1 01. So therefore the fundamental component of the thyristor T1 is equal to fundamental component of the output current only from 0 to T by 2. And the remaining it is 0. So this is maximum value of the output fundamental component of the output current. So if you want to find what is the average value of the fundamental component of the thyristor current, which is basically half a rectifier, so maximum value by pi. So I don't want max plus the maximum value of the fundamental component of the output current by pi. You want the RMS value of the fundamental component of the thyristor current, which is maximum value by 2. So I don't want max by 2. So if you want to find what is the fundamental component of the output power absorbed by the load, fundamental component of the average power absorbed by the load is equal to the RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into cos phi 1. Because both are in same phase, so phi 1 is equal to 0, so cos phi is equal to 1. So the RMS value of the fundamental component is simply we can get from the expression of the graphs from the expressions 4is r by root 2 pi and I got 1 RMS is equal to 4is by root 2 pi and cos phi 1 is equal to 1 because their phase difference is 0, so cos 0 is equal to 1. So if you multiply all these things, we are going to get the amount of fundamental output power consumed by the load. So if you want to find what is the fundamental displacement factor, which is cos phi 1, it is a phase angle between the fundamental output voltage and the fundamental output current. Both are in phase, so cos 0 is equal to 1. So total power across load. So what is the overall power consumed by the load, which is P naught is equal to I naught RMS square into R. So I naught RMS square into R is the thing which is consumed by the load. So therefore is equal to V naught RMS whole square by R. So this is the I naught RMS is equal to IS. So IS square into R is the overall is equal to IS square into R is the overall average power consumed by this load. So therefore the total power consumed by the load is equal to IS square into R. So the total power consumed by the load is equal to I naught RMS square into R is equal to V naught RMS square whole square by R. So now we are going to learn about the C load. So we have replaced the resistor load by the capacitor load. So this is the current source inverter, voltage source inductance. So this is T1, T2, T3 and T4. We are going to keep a capacitor C. Just we have replaced the resistor load by the capacitor load. So the capacitor output voltage is V naught of T and the capacitor output current is I naught of T. So this is the source current IS and this is the thyristor current IT1. So this is the input voltage plus or minus VIN and this is the output voltage and the output current. As I have already told you, irrespective of the load, the output current waveform will be always same waveform. So from 0 to T by 2, T1, T2 are going to conduct. So therefore, I naught is equal to IS. So I naught is equal to IS. Whereas from T3, from T by 2 to T, T3, T4 are going to conduct. So if you analyze, I naught is equal to minus IS. So minus IS. So this is the waveform that you are going to get. So if you are going to apply a DC current source, DC square waveform or DC current source across a capacitor, the voltage waveform will be a ramp waveform and it is going to lag by 90 degree. So whenever you apply a constant current source across a capacitor, it will be basically a ramp waveform. So therefore it is going to lag by 90 degree. So this is the triangular waveform. We are going to get the output voltage. We are going to get the output voltage as the triangular waveform. We are going to get the maximum value of plus V naught max and minimum value of minus V naught max. It is going to lag the output current by 90 degree, means T by 4 time. So now we are going to do some analysis. I already told you from during 0 to T by 2, T1, T2 are on and T3, T4 are off. So therefore, if you analyze, we are going to get I naught is equal to Is and V naught is equal to VIN. Whereas from T by 2 to T, T2, T4 are on, whereas T4, T1, T2 are off. So therefore, I naught is equal to minus Is and VIN is equal to minus V0. So this is the thing that we are going to do. So natural computation or load computation is possible for thyristors. So in this case, the natural computation or the load computation is possible for the thyristors because whenever the T3, T4 are on, the capacitor voltage is going to be, it is going to produce a negative voltage across the T1, T2, so they are going to get turned off. Similarly, whenever the T1, T2 are on, this capacitor voltage is going to produce a negative voltage across the T3, T4 and they are going to get turned off. So therefore, simply we can say that natural combustion or the load combustion is possible for the thyristors in this case. And I have already told you the output current is a square waveform, then the output voltage is a triangular waveform and it lags by 90 degree. So if you apply a square waveform across the capacitor, the output voltage will be triangular waveform and the output voltage is going to lag the output current by 90 degrees for a pure capacitor. So if you want the expression which is output current is equal to 1 by C integration of output, so output voltage is equal to 1 by C integration of output current into dt. This is the nature of the output voltage and output current across a capacitor. So I have already told you from 0 to T by 2, I have already told you VIN is equal to V0. So it is same as a V0. Similarly from T by 2 to T, VIN is negative of the V0. So it is a negative of this one. So you can see clearly the fundamental frequency of the input voltage is twice the fundamental frequency of the output voltage of the output current. So the fundamental frequency of the input voltage is twice the fundamental frequency of the output voltage of the output current. So now I want to draw what is the nature of the thyristor T1 current. So T1 is connecting only from 0 to T by 2. So after that it is off. So whenever it is open, the current is 0. So from 0 to T by 2, T1 is connecting. So when T1 is connecting, I naught is equal to IT1. So I naught is equal to IS in this case. So it is IS. So this is the graph that you are going to get. So I have already told you at T by 2, this V naught, the capacitor voltage is positive value. So at this instant, I am going to turn on the T3, T4. If I on the T3, T4, this V naught is positive. So therefore, as the V naught is positive, it is going to produce a negative voltage across the T1 and T2. So they are going to get turned off. So from T by 2 to T by 4, V naught is positive. So therefore, if V naught is positive, means it is going to produce a negative voltage across the T1, T2. So they are going to get turned off. So from T by 2 to T by 4 means an angle of pi by 2. For angle of pi by 2, a circuit means a negative reverse voltage is going to apply across the T1, T2. So circuit turn of time of a thyristor is equal to omega Tc is equal to pi by 2. So Tc is equal to pi by 2 omega naught. So for this much amount of time, the thyristors are going to face a reverse voltage. Similarly here, at this instant, T2, T4 are conducting, but I want to turn on the T1, T2 after this. So when the T1, T2 is turned on, the capacitor voltage is a negative. So therefore, it is going to produce a negative voltage across the T3 and T4. So they are going to get turned off. Automatically T3, T4 are going to get turned off. So no need of forced computation to turn off thyristors. By load combination only they are going to get turned off. So the frequency of the fundamental frequency of the input voltage is twice the fundamental frequency of the output voltage or output current. So F0 is called the fundamental frequency of the output voltage of the output current. So omega naught Tc is equal to pi by 2. So Tc is equal to pi by 2 omega naught. Means for this much amount of time, the thyristors are going to face a reverse voltage across them. So conduction angle of each thyristor is nothing but pi. So conduction angle of each thyristor in terms of time, which is pi by 2. So from the graph, I can easily say that the average value of thyristor current is equal to Is into T by 2 by T, which is Is by 2. So the RMS value of thyristor current T1 is equal to Is into amount over T by 2 by T, which is Is by 2. So I want the expression of the output current. It is a periodic signal. So I naught of T is equal to sigma and is equal to 135 to infinity 4 into peak values Is by N pi into sin 1 omega naught T. So V naught of T is equal to I naught of T into minus jxc. So minus jx is equal to minus j by n omega naught c. So if you want to if you substitute this expression here, we are going to get naught of t is equal to sigma n is equal to 135 to infinity 4 is by n pi into 1 by n omega naught c into sin of n omega naught t minus n pi by 2. Because that voltage across the capacitor is going to lag the current by 90 degree. So this is the expression that we are going to get. If you want to know what is the fundamental displacement factor, which is cos phi 1 is equal to cos of phase angle between the fundamental output voltage and the fundamental output current. As the phase difference is pi by 2, so cos of 90 is equal to 0. So I want to find what is the fundamental component of the average power consumed by the load. So this RMS value of the fundamental output voltage into RMS value of the fundamental component of the output current into cos of phi 1. As phi 1 is equal to 90, so cos 90 is equal to 0, so overall is equal to 0. The fundamental component of the reactive power consumed by the load is equal to RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into sin of phi 1. As phi 1 is equal to 90, so sin phi 1 is nothing but 1. It is the product of the RMS value of the fundamental output voltage into RMS value of the fundamental output current. These two values we can get from the expressions. So now I want to draw what is the fundamental component of the thyristor current. The fundamental component of thyristor current means from 0 to t by 2. So T1 T2 are connecting, so therefore IT1 is equal to I0. So fundamental component of thyristor current is equal to fundamental component of the output current in 0 to t by 2. But after the t by 2, the T1 is off, so therefore current is equal to 0, so therefore its fundamental component is also equal to 0 in this case. So its average value is maximum value by pi, and the RMS value is equal to maximum value by 2. So the I01 max is equal to, it's the fundamental component, the maximum value of the fundamental component of the output current, which is 4Is by pi. We can easily get from the expression. So the average value of the fundamental component of the thyristor current is equal to maximum value by pi, which is I01 max by pi. The RMS value of the fundamental component of thyristor current is equal to maximum value by 2, which is I01 max by 2. So from 0 to t by 2, that I want to write what is the expression of the capacitor voltage and the capacitor current. So I0 of t is equal to C into d divided by dt. But I0 of t is equal to Is in this case. So Is is equal to C into the amount of change is 2 V0 max by t by 2. So if you solve this one, we are going to get V0 max is equal to Is into t by 4C. So this is the maximum value of the output voltage, which is plus V0 max and minus V0 max. So I want to find what is the RMS value of the input voltage. See, input voltage and the output voltage both are of same shape. So the output voltage is a triangular in shape, whereas the input voltage is a clamp shape. So both are going to have the same RMS value. So the RMS value of the input voltage is equal to RMS value of the output voltage is equal to maximum value by root 3, so which is V0 max by root 3. So the RMS value of the input voltage is equal to RMS value of the output voltage is equal to V0 max by root 3. So now we are going to connect the parallel RC load. So basically we are going to connect the parallel RC load for this current source inverter. So this is the circuit diagram, which is voltage source inductance, and this is the T1, T2, T3, T4. So this is the input voltage plus or minus VIN, and this is the source current IS, and this is the parallel resistors. So parallel RC load. So this is the output voltage plus or minus V0 of t, and the output current is I0 of t. So now we are going to basically analyze this circuit. I have already told you, irrespective of the load elements, always the output current waveform will be always same waveform. Only the output voltage is going to get changed based on this load. So this is basically the polarity of the input voltage. So I have already told you the output current will be in this format from 0 to t by 2. T1, T2 are on, so therefore the output current is equal to plus Is. Whereas from t by 2 to t, the output current is equal to minus Is. So minus Is. And also I have told you from 0 to t by 2, whenever the T1, T2 are connecting, the output voltage is equal to plus Vn. Whereas the from t by 2 to t, so T3, T4 are connecting, so therefore Vn is equal to minus V0. That is the thing that you need to always remember. So now we are going to basically analyze this circuit. C is connected in parallel with R load. So C is connected in parallel with R load in order to make natural combustion for the thyristors. So I have already told you, in the R load, if you keep R load, then there is no natural combustion is not even possible for the thyristors for R load. Whereas for capacitor load, yes, the natural combustion for the thyristors is possible. So because of this reason only, so because I want the natural combustion in R load, I am going to keep a capacitor in parallel with the R load. So therefore, C is connected in parallel with R load in order to make natural combustion for the thyristors. So now the natural combustion is possible for this combination. When we apply constant DC current source across a parallel RC load, then voltage across the capacitor will be exponential and have the output current by phi 1. So I have already told you, whenever you apply constant DC current source across a parallel RC load, so it is basically a capacitor load. So basically it is going to act like capacitor. So for a capacitor, if you apply constant DC, you can say that it will be exponential. So voltage is going to lag the supply voltage by some amount of angle phi1. So here when we apply constant DC current source across a parallel RC node, then voltage across the capacitor will be exponential and lag the output current by phi1. So therefore now the output voltage is going to lag the output current by some amount of angle phi1. So therefore minus Vm plus Vm, and it's like exponential, it is going to occur. So this is phi1 plus this is pi plus phi1. So you can see clearly, so at t by 2, you can see clearly that voltage is positive. So voltage is positive means whenever the T3, T4 are on, so whenever the T3, T4 are on, V0 is positive. So therefore V0 is positive means it is going to reverse bias the T1, T2. So therefore the T1, T2 are going to face now reverse voltage, or the load combustion is possible for this case. So the circuit turn off time is, the phase angle is phi1. So up to phi1 only they are going to face a positive voltage means reverse bias voltage. So phi1 by omega naught is the circuit turn off time for this thyristor. So natural computation is possible to turn off the thyristors. Circuit turn off time is equal to omega naught, Tc is equal to phi1. So Tc is equal to phi1 by omega naught. So now basically I am going to analyze this circuit. From 0 less than or equal to t less than or equal to t by 2. So in this case I can see that clearly that T1, T2 are connecting. So whenever T1, T2 are connecting, T2 are connecting, I can draw the figure, I can draw the circuit again in this fashion. This R and C are in parallel, and this is the V0 of T, and this is the capacitor voltage plus or minus Vc of T, both are equal, and this is a supply current Is, it is the current source. So Is is the current source, so therefore it is going to divide into two formats. The resistor current is IR of T, and this is the source, and the capacitor current is IC of T, and this is the output voltage V0 of T, and Is is nothing but I naught of T. So now I can convert this circuit into a Thevenin circuit. I can replace the circuit to Thevenin circuit, which is the voltage source is equal to current into, which is R. So Is into R. So Thevenin voltage is Is into R, and the Thevenin resistance is R. So therefore this is the Thevenin circuit across the capacitor. So this is the Thevenin voltage is equal to Is into R, and the Thevenin resistance is R, and this is the capacitor C. So this is the capacitor current IC of T, and the capacitor voltage is Vc of T. So capacitor voltage itself is equal to output voltage. So now what is the initial value? So initial value of the capacitor voltage, you can see clearly capacitor voltage initial value is equal to output voltage, it is equal to minus Vm. So therefore V0 of 0 is equal to Vc of 0 is equal to minus Vm. What is the Vc of infinity? So Vc of infinity is equal to, if you leave it for infinite time, this capacitor voltage is going to charge to Is into R. So Is into R is nothing but V I am going to consider. So the capacitor in infinite voltage is nothing but plus at infinity the capacitor is going to charge to a source voltage, which is equal to Is into R is equal to T. So now I am going to basically apply this formula, which is Vc of T is equal to F IF plus minus. So Vc of infinity plus Vc of 0 minus Vc of infinity into e to the power of minus T by tau. So Vc of infinity is equal to Is into R, which is equal to V, and Vc of 0 is equal to minus Vm, and tau is equal to R into C. So R into C. So therefore tau is equal to R into C. So now you are going to get the expression of Vc of T, but I want the current Ic of T. So Ic of T is equal to C into dVc of T by dt. So after that, if I know Ic of T, then what is IR of T? So IR of T is equal to Is minus Ic of T, because by applying the KCL in the circuit, we are going to get IR of T is equal to Is minus Ic of T. So if you apply all the values, finally we are going to get the capacitor voltage is equal to Vc of T is equal to V into 1 minus e to the power of minus T by tau minus Vm into e to the power of minus T by tau. So this is the thing that we are going to get. And similarly, Ic of T is equal to C into dVc of T by dt. So if you solve this one, we are going to get e to the power of minus T by tau into V plus Vm by R. So at T is equal to T by 2, at T is equal to T by 2, Vc of T by 2 is equal to Vm. Then we get. So here from the graph you can see clearly at T is equal to T by 2, we are going to get Vc of T by 2 is nothing but output voltage is equal to Vm. So now in this expression, at T by 2, at T is equal to T by 2, so at T is equal to T by 2, we are going to get Vm. So if you substitute all these things in this above expression, finally we are going to get V plus Vm is equal to 2V by 1 plus e to the power of minus T by 2 tau. So this is the thing that you are going to get if you substitute this expression in this equation. So finally Vc of t is equal to, so the standard equation which is Vc of t is equal to V is equal to Is into R 1 minus e to the power of minus t by 2 minus Vm into e to the power of minus t by 2. So Ic of t is equal to, now here t to the power of minus t by 2, which is now V plus Vm by R. So V plus Vm by R is nothing but, so Ic of t is equal to this expression with e to the power of minus t by 2 into V plus Vm by R. But V plus Vm is equal to 2V by 1 plus e to the power of minus t by 2. But here divided by R, so V is equal to Is into R, so R cancels. So finally we are going to get Ic of t is equal to 2Is by 1 plus e to the power of minus t by 2 into e to the power of minus t by 2. So just do V plus Vm substitute here, and if you simplify, we are going to get this expression. So what is IR of t? IR of t is equal to Is minus Ic of t. So you know Is minus Ic of t, substitute here, we are going to get this expression. So now I want to find what is the circuit turn off time. So now capacitor voltage, just now we have figured out the capacitor voltage is equal to Vc of t is equal to, which is V into 1 minus e to the power of minus t by 2 minus Vm into e to the power of minus t by 2. I want to find what is the circuit turn off time. At what time the capacitor voltage is equal to 0? At what time the capacitor voltage is equal to 0, I want to figure out. At what time I want to find what the capacitor voltage is equal to 0. Then we get, if we substitute t is equal to Tc, at the time the capacitor voltage is equal to 0, we are going to get, to substitute here, we are going to get finally Vm by V is equal to 1 minus e to the power of minus Tc by 2 by e to the power of minus Tc by 2. So let me ask this equation 1. Similarly, same equation we take again, capacitor voltage is equal to V into 1 minus e to the power of minus t by 2 minus Vm into e to the power of minus t by 2. At Vc at t by 2, what is the value? At capacitor voltage at t by 2 is equal to Vm. Then we get, so at t by 2, the capacitor voltage is equal to output voltage is equal to Vm. So then we are going to get like this, Vm by V is equal to 1 minus e to the power of minus t by 2 by 1 plus e to the power of minus t by 2. These both the equations are equal, so we are going to equate these two equations. So these both equations are equal, so I am going to equate these two equations. Then I am going to get the circuit turn of time is equal to Rc into ln of 2 by 1 plus e to the power of minus 1 by 2 Rcf. So Tc is equal to Rc into ln of 2 by 1 plus e to the power of minus 1 by 2 Rcf. So 2 Rcf. So this is the value you are going to get the circuit turn of time. So for this much amount of time, the transistors are going to face a reverse voltage across them. You can see clearly, for this capacitor voltage, we have got the expression of this capacitor voltage from 0 to t by 2. So we got this expression. So now, see T1, T2 are on at 0. But before that T3, T3, 4 are on. So whenever T1, T2 are on, the capacitor voltage is negative. So it is going to give a reverse voltage across at T3, T4. They are going to get turned off. So for this much amount of time, from 0 to 5 on, they are going to face a reverse voltage across T3, T4. We are going to find this value of Tc. So Tc is equal to, this is the expression that we have already got. So Tc is equal to Rc into ln of 2 by 1 plus e to the power of minus 1 by 2 Rcf. So this is a thing that you need to always remember. So by this lecture, we have successfully completed some of the important formulas of the inverters in a very detailed manner. And if you like the content of our channel, then please to like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, a direct notification comes on mobile. If any information needed in our lectures, then please do comment in the comment section. We will definitely include all those information in the coming lectures. Thank you so much for watching this lecture. This one, take care. Bye bye.